Hey everybody, this is Mr. Beckstrom. Today I'm taking a look at another example from section 4.5. I'm going to do parts A and B. This is number 8. It says squares with side length x are cut out of each corner of a rectangular piece of cardboard measuring 11 by 7. So I'm going to put a little cardboard, so I have 11 by 7 here. The resulting piece of cardboard is then folded into a box without a lid. Find the volume of the largest box that can be formed. So we're basically going to be cutting like a square out of here, cutting a square out of there, cutting a square out of here, and then cutting a square out of there. And then we're going to fold up these pieces here, so everything but the squares that we just cut out, to make a box without a lid. And we want to maximize the size of the volume, or the volume here. So the volume is going to equal to what? Well, the volume is normally length times width times height, right? Length times width times height. So in this case, what is it going to be? Well, if we call the side length of x, so if this is x, and this is x, and that's x, and this square side length is x, 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 right? So this length here is going to be 7 minus x minus x. So that's going to be, that side there is just going to be 7 minus 2x. And then we're going to have this length here, which is just going to be 11 minus x minus x. So that's going to be 11 minus 2x. And then the height, when you fold this thing upwards, is just going to be that x length there, so times x here, because we're just folding it up at the crease right here. So here's going to be the volume all in terms of x. So it'll be 7 minus 2x for this length here, 11 minus 2x for this length here, and then the height will just be x. All right, so we can write this, if we multiply that together, that's going to be, let's say, 77, so yeah, negative 22 minus 14, so 32, 36, so minus 36x plus 4x squared plus 4x squared. Let's see. 22, 32, yes, and it's this whole thing times x. All right, so this is going to be equal to 4x cubed minus 36x squared minus 36x squared plus 77x plus 77x. And let's take a look at the interval that we're looking at. So we definitely can't have an x value that's smaller than 0, so we're going to go from 0, and the largest possible x is half of that 7, right? Because we can't go more than half of this length. We can't go more than half of 11 either, but we'll take the smaller of the two sides there. So 3.5 will be the values that we're looking for, because anything larger than 3.5, then we're going to go through the center, and then it wouldn't make sense for this side of 7 here. So some value between 0 and 3.5. Now remember, once we get our equation here, our objective equation, in the form in one variable, then what we're going to do is we're going to take the derivative of it and set that derivative equal to 0. And what that's going to do is that's going to, remember, the derivative of a function will show us the where the slope of the tangent lines, or it's going to give us the equation of the slope of the tangent line. If we set it equal to 0, we'll see all the places where it has a tangent line with a zero slope. In other words, it'll have a horizontal slope. And horizontal slopes show us where the peaks and valleys are. And that's where we expect the high points and the low points to be. So what we'll do is we'll need to check the endpoints, which in this case, the endpoints aren't really going to make sense, right? Because if we do we'll need to check the endpoints. We'll need to check the endpoints and then any of those critical values that we find between 0 and 3.5. All right, so let's find the derivative first. That should be the easy part. So the derivative of this is equal to 12x squared minus 72x, just using the power rule, plus 77. All right, now I am unsure whether or not that is factorable, but instead of trying a bunch of stuff, I am just going to use my calculator for this. So what I'm going to do here is come over here, and in my y1 equation, I'm going to go ahead and put in the original function there. So 4x cubed minus 36x squared minus 36x squared plus 77x plus 77x. And in the second one, I'm going to put the derivative function here. So that is 12x squared minus 72x minus 72x plus 77. And remember what I said we're going to do. We're going to take this equation here. So 12x squared minus 72x plus 77. We're going to set that equal to 0. All right, so I just really want to find the zeros of this function, which I'm going to go ahead and do by using my calculator here, just to kind of make this a little bit easier. All right, now you could also do what? You could use the quadratic formula, or you could try to factor that, which, like I said, I'm not sure if it's factorable, but it doesn't look like anything I really want to try to factor. So I'm going to go to, let's go ahead and graph. And I've got the 2 on there, so let's just show the derivative one right now, just so I'm not looking at the other one here. Oops. And so to turn the other one off, I'll just do that. So go back to graph, and it looks like it touches here and about here. So to find the 0 of it, you do second calculate, and we're going to do the 0. And it says I need a left bound, so I'm going to check this left one first. So I just put the cursor anywhere on the left side of this value here, hit enter, and then I need a right bound. So I have to put somewhere between these two intercepts here. So that looks good. Enter and enter, and it looks like it's going to end up being some kind of irrational number here. So probably a good thing I didn't try to factor that. So I'm going to use 3 decimal places. So that's 1.393. So x is equal to 1.393. All right, and then I have another one there, so let's go ahead and check that one as well. So second calculate, the 0 here, and a left bound. This time I'll go somewhere in the middle here, and the right bound, I'll go over here and enter, and that one looks like 4.607. So 4.607. And as we see, there's only one that is in the interval that we care about in our domain. So this is the critical value. Now, in this case, if our x value is 0, that's really not going to make sense, right? Because now we're not even going to be able to fold the box at all, because we're going to have a 0 height of this box. And if we let the x value be 3.5, then the width here is going to be 0. So then the length times width times height with a 0 there is also going to give us a 0 volume. So both of these endpoints aren't going to work. So the only value that's going to work here is this one, the 1.393. So that's the x value, the side length, that is going to maximize my volume. So now all I've got to do, I think I have it saved in here as my y1. So to go ahead and put it in there, I am going to go to vars, pull up my y1 variable, and let's go ahead and evaluate that at 1.393. And it gives me a value 48.271. So the volume is equal to 48.271. And let me double check that, 48.217, excuse me, 217. And this is going to be cubic feet. So feet cubed. All right, so this is how you do part A here. All right, so for the second part here, I'm going to try to give myself a little bit more space. For the second part here, it says, suppose that in part A, the original piece of cardboard is a square with side length S. So now we have some kind of just a big square with side length S, and we're still doing the X things here, right? We're still carving this out. So X for the length of the side of the little squares here. It says find the volume of the largest box that can be formed in this way. All right, so the big side length of the whole thing is S, and then the little lengths are X. So in this case, our volume, our length times width times height. So our length here, this part here is the whole S minus X for the length. So that's just going to be S minus 2X. S minus 2X. Our width is going to be this whole side, which is S minus X minus X, so same thing. S minus 2X. And our height will be the same as before. It'll just be that X value there. So length times width times height. So let's go ahead and multiply this thing out here. So you're going to get S squared, right? That's S times S. And then you have negative 2SX plus negative 2SX. That's going to be minus 4SX minus 4SX, and then plus 4x squared plus 4x squared, and then we're going to have to take this whole thing and multiply through by x. So this is going to be equal to, and I'll put it in order, this is 4x cubed. All right, and then I have a, let's see, I have a minus 4s x squared, and then I have a plus s squared x, s squared x. All right, remember, we're treating s as though it were a constant and not a variable when we're doing our differentiation. So there's a difference there. We're not differentiating it as a variable. We're treating it like a constant. So it's going to make a difference, and we'll see how in just a second here. So once I have this out here, let me just double check that. We can now take the derivative of the volume like we did before. So this is going to be 12x squared. And 4s is just a constant, so you bring the 2 out there. So that's going to be minus 8sx. And the x will just drop off, so this is just going to be plus s squared. Plus s squared. All right, so now, well, we have this thing, and we're going to want to set this equal to 0, just like we did before. So 12x squared minus 8sx plus s squared is equal to 0. And now I'm going to do my a, b, and c, because I'm going to go ahead and do the quadratic formula. So my a is just the coefficient in front of my x squared, which is 12. My b is equal to negative 8s, negative 8s. And my c is just going to be s squared, s squared. All right, so now it's really just kind of going through and figuring this out, right? So this is negative b. So my x answers are going to be equal to negative b. So it's negative 8s. So that's 8s plus or minus the square root of b squared. So that's 64s squared. 64s squared minus 4 times a times c. So 4 times 12 is 48 times c is s squared, so minus 48s squared all over 2 times a, all over 24. All right, so hopefully I got enough room here. So I've got 8s plus or minus. So 64s squared minus 48s squared is going to be 16s squared. And the square root of that, remember s squared is a positive number. So s is going to end up being a positive number. So this is plus or minus 8s. Plus or minus the square root of 16s squared, which is plus or minus 4s. Right? All over 24. 24. So this is equal to, let me see, this is 8s plus 4s is 12s over 24. 12s over 24. And 8s minus 4s is 4s over 24. 4s over 24. And those will reduce down to s over 2 and s over 6. So what this means is that for any square size cardboard that we start with of size S, that we can maximize the volume. We can maximize the volume by using one of these figures. Now let's try both of these back in here. Notice if I put an s over 2 back in here, 2 times s over 2 is just s, and s minus s is 0. So there you get a 0, and a 0 volume doesn't work, so we can leave this one out here. So we're going to use the s over 6. So an s minus an s over 6. So let's look at that one. I'm kind of out of space here, but I'm going to do s minus s over 6. So that's really 6s over 6 minus s over 6, which is, oops, wait, that's 2 there. Let me fix that. I'm just got too much stuff written over here. So let me write this again. This is going to be 2 times x, so that's s over 6. So that's really s over 3. So we should have, excuse me, 3s over 3 minus, because 2 times s over 6 is s over 3, minus s over 3 is equal to 2s over 3. So that one does work. So this is your answer right here, s over 6, which means that your sides will be 2s over 3, 2s over 3, and s over 6. So 2s over 3, 2s over 3, and s over 6. All right, I know this was kind of complicated. I hope it made a little bit of sense. And if you have any questions, let me know. Thanks. Bye.